There is one other result that we are going to need, and that is something that you already know, and this is the following. Suppose X follows a normal mu sigma square I distribution and R is any orthogonal matrix. In that case, R of X, R times X must follow again a multivariate normal n-dimensional with mean vector R mu, and the variance covariance vector will still remain sigma squared I. That is very easy because R times R prime will be equal to the identity matrix. Now the importance of this is the following, that if you take some particular normal vector, multivariate normal vector, and express it in terms of a different orthonormal basis other than the Euclidean basis, still the components will remain independent and homoscedastic. And if your mu's are all zeros, in that case they will actually remain IID normal 0, 1 also, irrespective of what orthonormal basis you are choosing. So so we are going to need the concept of projection very much in this discussion. So let us familiarize ourselves with the geometry and the linear algebra underlying it. So whenever we think of projection, it's a good idea to visualize the entire thing as projecting a vector in R3 onto the xy plane. So we have the xy plane here and we have some vector projecting here, that's my origin. This is pretty simple. We just drop a perpendicular from the tip of the vector onto the xy plane and we get this. So the geometry should be pretty clear in case when we have got the screen onto which we are projecting, the subspace onto which we are projecting as the xy plane. Now how do I do the mathematics with it? That's pretty simple also in this case. So I started with a vector. If I call that x, y, z, then I just split it up into two parts, x, y and z. X, y is the part on the xy plane and z is the part that is perpendicular. So basically I have masked out the z using a 0 in that projected part, that is the yellow thing, and masked out the remaining things and kept z only visible in that perpendicular thing. Now if I want to think of it as a linear algebraic way, we can think of it like this, that we have got this Euclidean basis vector. So I have got these two vectors, the x thing and the y thing, the E1 and E2, they are along the xy plane, and E3 is sticking out of this, and we basically took the component of my cyan vector, my original vector, in the E1 direction as well as in the E2 direction, and then kept only those two to get my projected thing. Then I took the component of the cyan vector along the E3 direction perpendicular to the plane, and that gives me my orthogonal part. Now precisely the same thing works even if you are working with something else which is not the xy plane. The only idea is you start with this fellow and then you take your orthonormal basis in a way such that the first two or the first few of the vectors are along the space onto which you are projecting, and the remaining are sticking out perpendicularly from it. Even then you can do the same thing. So the basic idea is like this: you start with an orthonormal basis of this space onto which you are going to project, and suppose I call them these white vectors, and there may not be two in general, there may be a number of them, and then you extend that to an orthonormal basis of the entire space. So you append some extra stuff. I have shown them with red. So you have got this, the entire bunch is an orthonormal basis of entire Rn, and then you find the components of these things along each of the directions. So you stack them row wise in this way and multiply the cyan vector, that's your target vector, your original vector, and pre-multiply it with that matrix. So what happens is that the first entry of this result will be inner product of this vector with that vector. This is lying horizontally, that is vertical. Since this is an O and B, so that will give you the length of the component along, by length I mean the signed length, along the first vector. In our example it is x. Similarly for the next one it will be y. and the last one it will be Z. And then you just keep the part corresponding to the white thing, that will give you the projection onto that space, and the part corresponding to the red thing, that extended part of the O and B, that will give you the projection onto the orthogonal space.